Hey everyone, we're Unit 7B and this is topic 2. So yesterday we talked about, or our last topic, we talked about how to determine whether or not a function was linear or exponential. Today we're going to talk about how to graph an exponential function. So that means we already know it's exponential, and how do we figure out what the graph looks like? So to start, we have here what looks like an exponential equation. And last class, we also talked about recursive versus explicit. This is an explicit exponential equation. And when we wrote explicit exponential equations, we talked about what these two parts meant. The a value is the y-intercept. And I'm going to write underneath there what that looks like on a table. It would look like this, 0, comma, whatever a is. The b value is the common ratio. And I'm going to write two things under there. The common ratio is what we multiply by. That's one way to think about it. The other thing to think about is that it's the pattern. But the correct vocabulary is the common ratio, but this is how we think about it. It's what we multiply by, or it's the pattern. All right, example 1, we have 4 in parentheses 2 to the x power. So let's think about what these parts mean. 4 is the y-intercept. That means that a point on my graph is 0, comma, 4. And I'm going to go ahead right away and put that in the table right here where it belongs. 0, comma, 4. The 2 is the common ratio. And so what that means is that our pattern is multiply by 2. So 4 times 2 is 8. 8 times 2 is 16 times 2 times 2. And now I want to think about how I would go backwards. If I needed it to work backwards to fill in this table, going down I multiply by 2. So to work backwards, I would divide by 2. And I would get 2. All right, let's plot these points. So these points are -1, comma, 2. I'm going to make this a little bit bigger. 0, 4, 1, 8, and 2, 16. And now one thing about this is that these points do not look like they make a straight line. They don't make a straight line. They actually make a kind of curved line. So I'm going to connect these, kind of like connect the dots. Connect these. And what we're going to see is that exponential graphs exponentially go forward. They grow in that direction. And in the other direction, this graph kind of gets flatter. So I'm going to draw that it flattens out. And I'm going to write here, flattens, because this part of my graph is really flat. It looks like it goes almost like towards the x-axis, but this part grows really fast. All right. The next one, we have f of x equals 6, parentheses 1/2 to the x. 6 is my y-intercept. That means 0, 6 is on my table, right there, right? The other part that I know, I'm going to draw this in again, 0, 6. The other part is 1/2. That's my common ratio. And a common ratio of 1/2 really means that my pattern is divide by 2. We know that a fraction means that our pattern, our numbers are getting smaller. So when I work down my table, I'm going to do this, divide by 2. Divide by 2. So 6 divided by 2 is 3. 3 divided by 2 is 1.5. And if I worked backwards, this number would get bigger. I would get 12. So let's plot these points. -1, 12. 0, 6. 1, 3. 2, 1.5. So if we connect to these points carefully, now think about which side is going to get flatter. In the other example, it got flatter on, I can actually look at this, on the left side of the graph. But on this example, it looks like it's going to flatten out on this side. So I'm going to make this side get flatter. And this side is going to grow exponentially. It's going to grow very fast. Okay, the next part is this brand new word. And this comes up a lot more in Algebra 2, but we're going to touch on it right now. A horizontal asymptote is an imaginary line that our graph approaches at the ends. So imagine a line that our graph approaches, and actually our horizontal asymptote in this case, I'm going to draw it with a dotted line, is basically all along the x-axis. So our graph, if you look at it, it gets close to this horizontal line, this horizontal asymptote, but it doesn't touch it. It just gets very, very close to it. And it's the same thing over here. Our horizontal asymptote is this horizontal line right here that our graph approaches but doesn't actually touch. And this line, if I wanted to write an equation of this line, would actually be the line y equals 0, horizontal line at 0. So the first two questions here say equation of the horizontal asymptote. We're going to write that here, y equals 0, y equals 0. Now we're going to talk about the domain of these graphs. And both of these graphs actually have the same domain. The domain is how much space our graph takes up from left to right. You could think about it as the start and the end. Our graph has arrows to the left and arrows up and to the right, which means it goes on forever in both directions. That means the domain is negative infinity to infinity. And the same exact thing goes for this graph. It goes to the left and up, and it goes to the right forever in both directions. Arrow, arrow. So our domain is negative infinity to infinity. All right, now we'll talk about increasing and decreasing. So I'm going to go up to this little graph. I'm going to draw a little stick figure. If this man was walking along this graph, he would be going up. He would be increasing. So I would say that this graph is increasing, and it's increasing everywhere. Negative infinity to infinity. This graph never changes direction. It's always going up, 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 up. So it's decreasing, never. That's how we indicate that symbol means that it's not decreasing. All right, this graph is quite the opposite. From left to right, this graph is decreasing. If I would draw that same stick figure on the left, he is going down. So this graph is decreasing from negative infinity to infinity, and it is never increasing. All right, you guys should be doing your homework. I think that we're on homework number 2, so you can do that. Good luck.